Today, class, we're going to be learning about projectile motion. When you're launching a water balloon into the air, you're actually sending it into projectile motion. Essentially, it's free fall motion with a horizontal velocity component. And the same is true for a basketball when you're shooting it. You're actually launching it up into the air at an angle which has both a horizontal and a vertical component. And these two components work together to determine its actual instantaneous velocity at any one given point during the flight of the basketball. So with projectile motion, we now have an object that's moving in two different directions. And as such, one of the first things we want to do is we're going to have to break it down into both the horizontal and the vertical, or the X and the Y direction. Now we're going to focus in first on the vertical direction because, guys, this really is just free fall. Everything that's happening in the vertical direction is what we've already been learning about with free fall in one direction, as we've been looking at objects as they move straight up and down in free fall. If you notice in all the examples, all the balls and objects, when they left the person's hand, or as soon as they were in mid-flight, they were still under free fall conditions. And as such, the acceleration in the vertical direction is still going to be negative g, or negative 9.8 meters per second squared. Now, this whole time the object is in the air, even though it's moving horizontally, the vertical position is being governed by its acceleration in the y direction. And so, since we have a constant acceleration in the y direction, then all of the UAM equations will apply. And a lot of the strategies that we use to solve for those uniformly accelerated motion problems still holds true here. We're only going to be looking at these variables, though, in the vertical direction. We'll also look at some of these in the horizontal direction, but with respect to being able to transfer information from one to the other, right now we're just talking about the vertical direction. Okay, let's talk about the horizontal direction then. We are still ignoring air resistance. It's under free fall conditions, and that was one of the requirements to be in free fall, was we're ignoring air resistance for in this breathable vacuum. And if you think about it, if gravity is the only thing that's pulling down on the object as it's moving through the air, what is actually slowing it down horizontally? In the real world, we see it as happening as the air resistance that slows it down horizontally. But if we're in a vacuum, there is no air molecules to slow it down horizontally. So whatever the initial horizontal velocity component that an object is launched with, it will maintain that same horizontal velocity throughout the entire flight path until it hits the ground or hits another object. And so the horizontal velocity is going to be constant across the entire path of the flight while it's considered to be in projectile motion. Again, projectile motion is really just free fall with a horizontal component. Since we have a constant horizontal velocity, then the acceleration in the horizontal direction is going to be 0 meters per second squared. And that's going to be constant. So these two accelerations that you see on the screen that are in yellow, when you're solving these problems and you're breaking them up into the components, one of the things that you can fill in right away, knowing that it's a projectile motion problem, is that the horizontal acceleration is going to be 0 and the vertical acceleration will be negative g, or negative 9.8 meters per second squared. So there are actually three different types of projectile motion problems that we'll look at this year. And the first one is what's called an elevated horizontal launch. So the object's going to launch horizontally from an elevated platform above the ground. This could also be an object that's dropped from an airplane that's moving perfectly horizontal. There's a couple different types of examples, but this is one of the categories, a horizontal elevated launch. But before we look at the actual flight of this object in a horizontal elevated launch scenario, let's just look at the vertical scenario of what this would look like under vertical free fall conditions when an object was just dropped. And so what we see here is that the ball just drops vertically straight down. And it's exactly what we've been looking at already. Now I've indicated the vertical velocity vector here with red, and as you can see, as time goes by, the ball continues to gain velocity in the negative direction, gaining speed as it moves down because it's accelerating straight down towards the center of the Earth. Well, now we're just going to add a horizontal component to that. So the initial vertical velocity of that ball when it was dropped was 0. Well, an object that rolls off of a table, is launched by a cannon perfectly horizontal, is dropped from an airplane that's moving, these are all the same type of problem. The vertical velocity is going to be 0, but it will be starting with a horizontal velocity. And so this is what the actual path of the object is going to look like. All projectile motion will follow a parabolic motion. And in this case, we're just picking up the back half of it. And we'll look a little bit more about that in a second. But what you can notice right away is that the yellow vector, which is the horizontal velocity component, is constant. It is always completely horizontal, and it's never changing because there is no acceleration in the horizontal direction, so we wouldn't expect the velocity to change. But notice that as the ball is moving horizontally and dropping, it's gaining vertical velocity, just like the ball that was dropped in the first example that you can see to the left side of the screen. That velocity in the vertical direction is exactly the same at the same heights as it was if it was just dropped. But because it has a horizontal velocity, it's also moving in the horizontal direction as it's dropping. And that's creating the back half of this parabolic motion here. When we put these two together, we can find what is the resultant velocity vector. So when the ball was just dropped, its only velocity was in the vertical. Well, we add this horizontal component to actually find how fast the object, in this case a ball, is actually moving with. What's its actual speed? We need to combine the horizontal and the vertical velocity vectors. And so this blue resultant vector here is what actually indicates the true instantaneous velocity, speed and direction. Okay, so it's how fast it's moving, and it's also indicating the actual direction of its instantaneous velocity. As you can see, it's becoming more vertical with time because the vertical velocity vector is continuing to grow while the horizontal velocity vector isn't. So the resultant velocity vector is also starting to curve and get more and more vertical as it continues to gain speed in the vertical direction. The next example I want to take a look at is what's referred to as an angled launch from ground. So it's launched with an upward vertical velocity, usually at an angle relative to the ground. And so the first thing you want to often do is break it into its horizontal and vertical components. Now let's take a look at what happens. As you can see, the object takes this full parabolic shape here. And there's some things that you're going to notice right away. First off, the horizontal velocity is never changing. It's always to the right and it's constant, as it always has been that we just went through before. Now, let's take a look at the vertical velocities. Everything that's happening on the way up is just like when we were throwing the ball straight up in free fall conditions in a vertical direction only. As the ball continues to go up, the vertical velocity continues to get smaller. In other words, it's slowing down vertically. And that's because the acceleration, little g, is directed straight down, or negative 9.8 meters per second squared. And so that's what slows down the vertical velocity. Now if we look at the very, very top, we remember that when we were talking about throwing the ball straight up in the air, at the very top, when it reaches its maximum height, the vertical velocity is actually 0. But be careful. Is the ball not moving? Well, no, if it wasn't moving, then it wouldn't be moving to the right. But clearly it's continuing to move to the right, but the only velocity vector that it still has is its horizontal velocity. So a ball in projectile motion at the very top of its vertical path has 0 vertical velocity, and the velocity which is moving it is its horizontal velocity component. So everything that happened on the way up is now going to happen exactly on the way down, but in the opposite direction, just like before. The vertical velocity is going to get larger as the acceleration due to gravity now causes it to speed up in the vertical direction. And if you notice, this from the top down, this looks just like what we were looking at from a horizontal elevated launch, and that's because it is essentially the same thing. at least qualitatively. Obviously, numerically, things are going to be different per each problem, but the path that it follows and the concepts that what's happening is exactly the same. Now, at each vertical reference, just like with the vertical freefall problems, the vertical components at each vertical reference being the same height above the ground are going to be the same but in the opposite direction. So if you follow along all these dotted lines, the vertical velocity at each one of these vertical planes is the same magnitude but in the opposite direction. And since the horizontal component is constant throughout, well then the actual speed or velocity that the ball is moving with is also going to be the same at each vertical plane. Furthermore, let's say that the initial velocity that this ball was launched with was launched at 45 degrees above the horizontal. Well, when it lands on the ground all the way down at the other end at the same vertical height, which in this case would be right at the ground, the velocity vector would be 45 degrees below the horizontal. So there's symmetry on the way up. The vertical velocity and the overall velocity will be the same on the way up as it is on the way down, just with the change in direction, with the vertical velocity being down on the way down. There's another thing I want to point out right here, which is two things. That the maximum height that an object reaches in projectile motion is often referred to as the altitude. You've probably heard this reference for airplanes, and it really is how high it is above the ground here on Earth is what's referenced as the altitude. And then there's the range. And this is referred to as the maximum distance or the horizontal distance that an object has traveled for a given time period. And we'll find later that this is really a function of the horizontal velocity and how much time the object is in the air. So altitude and range. The last one I want to look at here is an angled launch, except this time it's elevated. So you're going to see a lot of the same concepts as the angled launch at the ground, but a little bit different because we're elevated. So again, we're going to have an initial vertical velocity that's going to be up on some angle relative to horizontal, and we're going to be looking at those, breaking those down into its horizontal and vertical components. And let's take a look at what the actual path of the object does. Again, the same parabolic motion that we would expect for projectile motion. In fact, everything that's happened that we just discussed on the ground is exactly the same thing for all the same vertical planes. So everything we just discussed for where the lines you can see are happening is exactly the same as if it was launched on the ground. However, since it is elevated, it has more time to continue for gravity to continue to work on it, causing it to accelerate even more and gain more vertical velocity. And so it will continue to speed up and just carry on from there. At that point, you no longer have the symmetry that's going on because that's past the point at which the ball was launched from. Some of the strategies that you want to use to try and solve these problems. Okay, you're going to want to make a drawing to represent the actual situation. Just like before, as I'll continue to harp, creating graphical representations will help you visually see and break down the problem, so you don't have to keep it all in your mind. So we're going to be breaking everything down into horizontal and vertical components, and we'll be working more with vectors and how we do that. The only thing that you can carry over from the vertical and the horizontal variables is going to be time. Time is a scalar, and it is really the only thing that is shared by both the horizontal and vertical. And this often is something that you're solving for in the problem and then plugging it into the other side. So if you're solving it for the vertical, then you're taking that time and plugging it into the horizontal to do something with it there, depending on what the nature of the problem is. You're going to need to follow the same UAM approaches that we've been working on. Okay, we're going to identify all of our known variables. We're going to just write out a chart of the 5 variables. In this case, we can do it for both, but we already know what the acceleration is going to be in the vertical and the horizontal. You're just going to need to just continue to use those strategies that we've already built on for UAM here in projectile motion, just now that we have a horizontal and vertical components to keep track of. You definitely want to make sure that your calculator is in degree mode. Okay, all of our angles are going to be based around degrees. We're not going to be working in radians, so be careful is that you may need to switch your calculator back to degree mode when we're working on physics problems. The acceleration in the vertical is going to be negative g, or negative 9.8 meters per second squared, and the horizontal acceleration is 0 meters per second squared. It's constant horizontal velocity, always. These things are absolutes. Because we're in free fall conditions and we are ignoring air resistance, these are two of the variables that you can write in even before you read the problem. So make sure you don't forget to include them and keep track of them. Guys, this projectile motion, we are layering in, and we do have an object moving in 2 dimensions now instead of 1. But this is really just a progression, right? We started on UAM and we learned how to use those 4 equations for constant acceleration. And we then applied them to free fall conditions when we had this negative 9.8 meters per second due to acceleration due to gravity, and we looked at all of the things that are happening with a ball in free fall flight in 1 dimension vertically. Well, all we're doing now is just adding a constant horizontal component to that equation, and that's what we call projectile motion. And if you think back about the uniformly accelerated motion equations, because of the fact that the acceleration in the horizontal direction is 0 meters per second squared, and the acceleration in the vertical is negative 9.8 meters per second squared. They're 2 different accelerations, and uniformly accelerated motion equations have to have a constant acceleration. So be careful not to take the vertical velocity and then say, well, I'm going to just put that into my horizontal side of the equations. That won't work because they have 2 different accelerations. Okay? The only thing that can be carried over across is time. Thank you, and I'll see you guys soon.